this is a drawing of the Milky Way. Can you guys see where the sun is in the Milky Way? Is it near the center? No, it's not. The sun isn't even near the center of the Milky Way. You know, basically, I always tell my astronomy students, if you ever think you're special, go study astronomy. You'll figure out that we're not very special. The sun is a rather ordinary star, one of 200 to 400 billion stars in the Milky Way. But galaxies come in all shapes and colors. Here's another galaxy. These are beautiful pictures from the Hubble Space Telescope of various galaxies. Here is an irregular galaxies. Right, these are called the fried egg galaxies for obvious reasons. These are actually two galaxies that ran into each other a few billion years ago. And you tend to get these ring structures when galaxies crash into each other. You get these beautiful rings. What do you think the name of this galaxy is? The Sombrero Galaxy, because it looks like a sombrero, right? It looks exactly like a sombrero. So all types of galaxies, they come in all shapes and sizes. They're giant accumulations of stars. Basically, if you look carefully enough, you find that the universe is made of galaxies. This is probably the second most famous picture taken by the Hubble Space Telescope. It's called the Hubble Deep Field. And what do you see in this picture? These guys up front, they can answer this. What do you see in the picture?
Stars.
No, none of those are stars. Planets. What are those things? Galaxies. You take a picture of some spot in the sky, and the way they took this picture is they said, oh, here's a dark spot in the sky, there's no stars in it, let's take a picture, let's gather light for 2 weeks to take this picture. And then what they saw was shocking. It was full of galaxies. There's about 1,500 galaxies in this one little teeny tiny spot in the sky that the Hubble Space Telescope can look at. So how many galaxies do you think there are in the whole universe? A lot. Excellent answer. A lot is a really good answer. You know, lots and lots and lots and lots and lots. Billions and billions of galaxies, each with hundreds of billions of stars. How big is the universe? Really big. Excellent answer. You're way too technical here. These guys have it better. Really big is a great answer. Really, really big. It's so big it's hard to comprehend. Hundreds of billions of stars in billions and billions of galaxies. That's a really big universe. It's a really big universe. Do you know where it came from? And how it got there? Do you know who this guy is? I know who this guy. Albert Einstein. See, you have a ringer here. That's okay. Yes, that's Albert Einstein. This is Einstein, the younger Einstein. We're typically used to seeing the older, white-haired Einstein. This is the younger Einstein. This was about 1915 or so when he began to think about where did the universe come from. He had just invented general relativity, which is a description of how gravity works, and he said, look, let me apply that to the universe, because on the grandest scale, gravity is the only thing that matters in the universe. All the other forces are either short-ranged or they depend upon charges that are plus or minus, and once you get big things, they're all neutral. So gravity is the only thing that mattered. And he said, look, the universe is full of galaxies, an attractive gravity. And if you put those two things together, there's only two things that can happen if that's all there is in the universe. Thing one, capture. The galaxy is captured by gravity. Here is the picture of the captured galaxies. They start out flying apart. I'll get to that. They're caught by gravity and it starts to pull them all back together again, just like the rubber band pulled my galaxy back towards where it came from. Eventually, that makes gravity get stronger and stronger and stronger, and everything you know about will be crushed together in a single point. What do you think we call that? It's called the Big Crunch, because that's what happens. Everything you know about is crunched in the Big Crunch. There's another possibility. Let me show you on the card here. See if we can make it work. This is the hardest part of my presentation. Get out of the way. It's going to come down that way. Escape. The galaxy managed to escape from gravity. Here's the cartoon. The galaxies go out. They're moving too fast for gravity to stop them, and so they run away. They're free. No crunch. Yay! The universe doesn't come to a horrible end with everybody crunched into a singularity, which may happen or may not. Who knows? That sounds great, right?
Right.
But what happens? Well, if the universe gets bigger and bigger and bigger and is flying apart, no new stars form, because stars can only form when it starts to get dense. So if the universe is flying apart, no new stars form. The existing stars start to burn out, and the universe gets colder and colder and colder, and eventually it freezes to death. What do you think we call that?
Cold?
The big freeze? That's close. That's close.
Ice storm.
Yeah?
The Ice Age.
The Ice Age is even worse, because the Ice Age is just here on Earth. It's the whole universe that freezes to death.
Big ice.
The big
Ice.
chill. The big chill. Everything we know about gets frozen in the big chill. Well, let me ask a question here. Do you notice either of these things happening? Is it getting colder and colder and colder?
No, it's getting warmer.
It might even be getting warmer. You don't notice that it's getting colder and colder. Is the universe crunching together? Do you see your neighbor's house heading towards your house?
No.
That even sounds crazy, right? No, you don't see any of these things happen. And that's what Einstein believed back in 1915, that the universe was not heading towards the big crunch or the big chill. Yet, if all you have are galaxies and gravity, that's all you get. There's no other possibility. So he said, look, we have to add something to the universe because we're not heading towards the big crunch or the big chill. Let's add this. And you thought it was just a box. Look what it does to my galaxy. What happens to it? Don't touch it. What happens to the galaxy?
It can't go away. It can't run away.
It sits there, right? It's not running off towards the big chill. It's not being crunched back towards the big crunch. It's sitting there static, safe, right? That, thus creating a static universe. Einstein called this tilt to the universe, the cosmological constant. And he said, that has to be there if we live in this universe that's not screaming towards the big crunch or the big chill. My story has a villain. Anyone know who the villain is? Scary looking guy, right? Scary looking guy. De Sitter is his name. So that's a lesson, by the way. Everyone remembers Einstein. People have forgotten the villain, De Sitter. Oh well. In any case, De Sitter said, hey, look, Al, there's no evidence for this tilt. This tilt is like anti-gravity. It would say, for example, if you set a bunch of stuff on the table and you waited a long time, it would all start to move apart. Have you ever seen that happen? No, no one had ever seen that happen. And he said, I don't believe in this cosmological constant. You have to go out and prove that there's a cosmological constant. He even suggested how to do it in a very famous paper. He said, go look at what the universe is made of, which is...
Gravity.
No, come on, remember? It was just a couple minutes ago. Come on, what's the universe made of? Galaxies, remember? Galaxies, just a couple minutes ago, galaxies. Go look at the galaxies and see what they're doing. If they're flying towards us, we're heading towards the big crunch. If they're flying away from us, we're headed towards the big chill. This is Edwin Hubble. The man the space telescope is named after. Probably the most famous astronomer of the 20th century. So famous we named space telescopes after him, etc., etc. He said, I can do that. I can go out and look at the nearby galaxies and see what they're doing. He made this diagram, very, very, very famous, called the Hubble Diagram. It shows the distance to the nearby galaxies, see them there, distance, and how fast they're moving away from us or towards us. And he noticed that except for a very few nearby galaxies, they're all moving away from us. And the further away they are, the faster they're moving away from us. He discovered the expanding universe. The conclusion was, Al, I don't know what you're smoking, but you're wrong. There's no cosmological constant. The universe is flying apart, but is it flying apart towards the big chill, right? Remember our big chill universe, there it goes, and it gets caught. Well, on the way out, it's flying apart, and then it slows down, stops, and starts heading back towards the big crunch. The idea is to figure out, to know what's going to happen, you have to know how strong the rubber band is, how strong gravity is. So you go out, and the idea is now go out and look and see how much stuff there is in the universe creating gravity, trying to stop it from heading towards the big chill. So we should do that. We should go out and count all the stuff in the universe, right? And then we'll figure out what's going to happen, right? You going to help me? I see some stuff there, some there, some there, some there, and there, 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 and there, and there, and there, and there, and there. And I'm quickly going to run out of time to count all the stuff in the universe, right? We better come up with some better way to figure out what's going to happen. About a decade ago, we came up with a better way. You guys can see this. Look closely. Do you see a galaxy there? Do you see something funny in that galaxy? What's funny in the galaxy? There's something. What is that something? Can you see what that something is? What does it look like to you?
Not a planet, right?
It's a bright star, right? There looks like there's a bright star. It might, if it were the sun, we'd be in a heap of trouble because that one bright star is almost as bright as the entire galaxy. That one star is as bright as 100 billion regular stars, like the sun. Does anyone know what kind of star that is? A superstar. Very close. It's a supernova. It's a star at the end of its life explodes, and for about 3 weeks, it glows as bright as 100 billion ordinary stars. And you can use those to make the modern Hubble diagram. And this was an insight of a bunch of folks who subsequently won the Nobel Prize about 10-ish years ago. Here was their Hubble diagram made with supernova. It looks a lot like Hubble's old diagram, unless you look very closely. I want you guys to look there very closely. Tell me if the line is straight or if it's curved. It is curved a little bit this way. You can tell if you put a straight edge on it, and you make the straight edge go through the beginning, and everybody up here is above. If you make it go through the end, everybody down here is above, and if you connect the two ends, the middle disappears. That's hallmark of being curved, and it's curved this way just a little bit. And you know what that means? It means not only is the universe expanding, it's expanding faster and faster and faster. There's some mysterious force out there that we call dark energy that's pushing the universe towards the big chill. It's not like Einstein's cosmological constant, but now it's stronger. You're going to have to get off that. It's now not holding the universe static. The stronger version is pushing the universe towards the big chill. We don't really know what dark energy is. It might be a stronger version of Einstein's cosmological constant, or it could be that I should have put a rocket engine on the galaxy and made it fly away. That's different than anti-gravity. Or maybe there's a new force, and I'd have put like a spring down this end to pull the galaxy this way. There's a possibility even exists that dark energy is getting stronger and stronger and stronger. Today it's pushing galaxies apart. Tomorrow it could start tearing galaxies apart. Then it would tear apart solar systems, stars, planets, all atoms. You know what that we call that if the universe ends with dark energy going wild and tearing everything apart? The Big Rip, obviously. If you'd like to know more, I might recommend this. This is The Extravagant Universe by Bob Kirshner. It's a layman's guide to cosmology. Bob was one of the discoverers of dark energy. What I find most fascinating about the book is his the total shock the scientists have when they realize they've discovered dark energy. Something is pushing the universe apart towards the big chill. I am a working astronomer, astrophysicist. I study cosmology, which is where did the universe come from, how did it get here, where is it going, etc., with exploding stars called supernova. And so I'm happy to answer any questions you might have about dark energy or anything else in cosmology. And I mean, I'll even entertain questions about just about anything as long as it's sciencey. Thanks. And let me turn this off because it's noisy. What's that?
Why don't you make a test like get dark energy and like wait a couple of years, and if the
So,
dark energy is getting stronger, it'll like break the jar or something.
so that's an excellent question, is why don't we try to look for dark energy here on Earth? The thing is, it's very, very weak. You only really see it on the scale of galaxies. So if you do experiments here on Earth, you'll basically, we have yet to devise an experiment sensitive enough here on Earth to be sensitive to the effect of dark energy. It's only on the scale of the distance between galaxies that we start to notice dark energy. So it's a great idea. People are actually actively thinking about how to do an experiment here on Earth that would tell us that dark energy exists. No one has come up with the answer yet.